Now let's look at the last example problem in this topic. This problem is called the palindromic path. It's a USICO problem. This is 2015 Open, so that's the last USICO competition of that season. It's bronze level, but this is I think this is the last competition before they introduced platinum. So bronze is more similar to silver nowadays. So in this problem, you are given a n by n grid of fields. Every field is labeled with a letter, and Bessie will walk from the upper top left corner to the bottom right corner, and every step he will go either right or downward. So then the path that traversed by Bessie can be will result in a string of letters. So this string of letters, we say it's a palindrome if when you reverse the string, it's exactly the same. So the question asks us to compute the number of different palindrome strings Bessie can form during her walk. So the yellow highlighted path illustrate one path that results in a palindrome. So the string that's resulted here is ABXDXBA. And for this test input, the output is 4, because there are 4 different words that can be formed, 4 different palindromic words that can be formed by walking from top corner to the bottom right. So ABX, this is one of them. The other is ABCW, CBA, and also ABCD, CBA. Oops. Also ABXZ, XBA. So I encourage you to pause the video and think about how you would solve this problem. The key is to see whether your solution would be guaranteed to pass given the size, given n can be as large as 18. Okay, now you have thought about the problem. Let's first think about some sort of naive solutions, and then see whether that will be efficient enough. So we can use recursive search to construct all the strings. So we'll construct basically all the paths. After we construct the paths, we have the string, and then we can check whether this is a palindromic string. So the question is, would this be efficient enough? So the question, I guess, alternative to the question is, how many paths are there? There is a precise formula depending on n. So if you don't know that, I encourage you to pause and think about that. It's a sort of interesting combinatorial thing. Let's first consider how many paths are there in this sample example. So the way to think is we need to make 6 moves in order to go from the top left to bottom right. And 3 of them will be moved to the right, and 3 of them will be moved down. So no matter which path you are, it's going to consist of 3 right moves and 3 down moves. It's just that these right moves and down moves do not have to be, they can be in some sort of combination of orders. Now, the number of ways of ordering them is therefore 6 choose 3, because there are basically 6 steps, and there are 3 ups, 3 move to the right. So you choose 3 position out of the 6, and then you put right move there. Then the other 3 position has to be the down move. So 6 choose 3 for this input. More generally, it's going to be n minus 1 times 2 choose n minus 1. because there's n-1 to the right and n-1 down moves. And for n equals 18, that's going to be a number that is too big. So let's look at how big it is. So if n equals 18, then what we are talking about is 34 chooses 17. So I have it here. So that is let's see how many digits. Okay, so that is 2 times 10 to the 9. So that's way that's more than the we can handle in a few seconds, because 2 to the 10 to the 9, and we have to do non-significant amount of computation for each of the paths. So that's not going to be fast enough. So then the question is, can we prune the search space? Are we repeating things that are that do not need to be, or do we have to examine all the paths? Can we throw away some of the paths before we look at them? So then one way to do it is we can, after we pass the middle, we can start throwing away branches if they're no longer palindromic. So for example, if we go A, B, C, D, and then the next one we go to X, then we don't need to go further because we know X does not match C. So similarly, if we go A, B, C, Z, then the next steps, if we go right with C and X, if we go down with C, X, neither of these would work. So we can throw them away. So this will prune away some of the search space. However, it's not clear this will be efficient enough. So in fact, it is possible to construct counterexamples so that this is not efficient enough if the algorithm is simply to search and then prune away while we are searching. So for example, one extreme case is we have the first one and the last one being 2 different letters, and then everything else is sort of symmetric across the diagonal line. So then we will find out that this is not a palindromic path only when we reach very end. So we still pretty much have to explore all the paths. So we want a better approach so that we don't really have to search through all the possible paths. So the key insight is the middle of the path has to be in the diagonal, has to be in this diagonal. So it's this DZ-DW diagonal. So for this example, when you walk 3 steps, you have to end at one of the diagonal. So then essentially we only need to do search from one direction, and when we can stop at the diagonal. So in fact, we can stop. Yeah, let's just stop at the diagonal, and then we can also remember which position we stopped at the diagonal. So there are 4. In this case, there are 4 diagonal positions. So we know that for these positions, let's say for this Z here, there will be a number of strings that stop here when we start from top left. There will be A, B, C, Z. A, B, X, Z, A, X, B, Z. So we store all of this information associated with this cell. Then we can do another search starting from the bottom right corner. And when we search the other direction, so then we get A, B, X, Z, A, X, A, B, X, Z, A, B, X, Z. So yes, because these are both B, these are both X, so we get just A, B, X, Z. So now we know all the strings that can end up here and all the strings can end up here. Now for each of the string we find, if we know, say we have A, B, X, Z, we can, if we know A, B, X, Z also exists from the other end, that gives us one palindromic path. So essentially we can use a set to store all the strings that can be formed from one direction, and then when we search from the other direction, every time we have a new string, we just do a lookup in the set. So then this way we only need to perform half of the search. So I think that every step we have two choices. If we are only going towards the middle, every step we can choose to go to right or down, and we go n minus 1 steps. So there are at most 2 to the n minus 1 such paths. So that means 2 to the 17. So 2 to the 17 is fine. It's less than 1 million. So it's actually it's around 100,000. So that's perfectly acceptable to perform that much search, and in fact to storing that much data, that number of strings, that's all within the normal limit. So these slides describe what I just talked about. So the two approaches that will not be able to pass if there are test case to a strong test case that exploit sort of come up with the worst case example for the algorithm. So that's it for recursive search.